Hey guys, today we're going to talk about electromagnetic effects on molecules, which ties into spectroscopy. You can see here that this is only 3 slides long, so this should go pretty fast here. I'm going full screen a little bit. Um, but we figured it kind of ties into with molecular shape and bonds and everything, so we'll kind of talk about that. It also ties into our last unit, which was atomic theory, um, but we'll talk about that. So this right here is 3 different types of electromagnetic radiation, so infrared, microwaves, and radio waves. And you can see that they all do something different to molecules. So infrared does a lot of stretching and vibrational motion. So they can either cause like bonds to bend in this form, so it kind of wobbles. They can cause them to stretch either symmetrically, so on opposite sides, symmetrically together, or asymmetrically, so one bond stretches and the other one doesn't. Um, so infrared causes bonds to stretch in some way. And so like every time you feel like if you put your hand under a hot lamp or whatever, like that's infrared light that you're feeling heat. This is heat. So as molecules heat up, they bend and they stretch in different ways, and that's um, why like uh, those heat lamps and stuff hurt your skin, because after a while they start causing the molecules that make up your skin to stretch and bend in different ways, and those bonds can kind of start to break or change if they absorb enough heat. Um, Microwaves, on the other hand, cause rotational motion, so they can either cause the entire molecule to rotate. So in this case, it's rotating around this axis. They can rotate this way around a different axis, and these are double bonds, so it wouldn't happen here. But if there were single bonds, it can also cause a single piece of it to rotate around a bond. Um, so water does that when you put it in a microwave. Um, you get the hydrogens start rotating this way around the bond. Um, but we'll kind of talk about that next slide. And then translational motion is what happens with radio waves. So radio waves don't have a whole lot of energy to them, but they're big. So uh, different like levels of radio waves will physically move molecules. Not very much, but enough that they kind of aggregate over time and they slowly move. Um, and I'm going to kind of show you that in a simulation here, so we'll pop that up. Um, so here you can see I have different light controls. So we'll start with microwaves. We'll throw nitrogen dioxide in on this whole thing too. Um, but if I turn this thing on and just start bombarding it with microwaves, well, you can see as it gets, every once in a while, absorbs one of those rays and it rotates. So that's that rotational energy. This is literally what your microwave does to things. Particularly, a microwave in a kitchen is designed to focus on water molecules. So it tries to heat up water molecules, which is why things with water in them heat up more evenly or better than things that don't have a whole lot of water in them. Um, so that's all microwaves do, is just that rotational energy. If we switch this to infrared, now, oh, there's the bouncy bouncy, so boing, 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 boing. Um, Again, it absorbs it and it causes, in this case, it's causing that bending thing to happen. I can do the same thing to water here, so there's water getting all excited. Boom, 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 boom. If we go to visible light, actually, I'll keep it on water. If we go to visible light, well, visible light's only going to affect things that absorb visible light. So water is clear, it's translucent. It doesn't really interact with visible light. Carbon dioxide, it's a clear, colorless gas, so it doesn't do anything. Oxygen, nothing. Carbon monoxide, nothing. Nitrogen, nothing. Ozone, nothing. These are all clear, colorless gases. Now, nitrogen dioxide, it will actually absorb visible light. So it will absorb a little bit of it. It glows, and then it emits that light. So um, visible light will be absorbed by things that have color to them. So, like plants, the reason they're green is they absorb green visible light and use it. Um, so, visible light only affects some molecules, and then ultraviolet affects most of these molecules pretty much the same way. Ultraviolet is usually enough energy to start breaking bonds. So you can see that when it absorbs it, it breaks that single bond and it snaps off. If I throw water in here, water doesn't actually absorb ultraviolet light very much at all, so it's pretty much fine. You need something higher energy, like X-rays, to do anything to water. Carbon monoxide, same general idea. Sorry, carbon dioxide, same general idea. Carbon monoxide, same thing. Nitrogen, same thing. Oxygen, same thing. So the gases in the air are pretty stable. They don't really absorb ultraviolet light. The one exception is we have ozone in the atmosphere. It does, and you can see it breaks that single bond when it absorbs it, makes O2, and that's why ozone in the upper atmosphere is nice because it absorbs some of this ultraviolet light so it doesn't hit us. So that's just a visual on what different things do. So going back to this here. So this kind of just is a breakdown of everything. Starting with microwaves, which of the list is the lowest energy. They cause rotation. It's located, the location of hydrogen atoms within a molecule specifically is what like your household microwave does. But basically it just does rotation. So it does locate hydrogen atoms. You can use it for a few other things. But for the most part, microwaves aren't used as frequently. Infrared is used quite a lot in spectroscopy, particularly organic molecules. So it changes the vibration of the bonds. So you can analyze the vibration of the molecule at different locations to figure out what parts are visible in there. So like, oh, look, you see this vibration. That means that there's a methyl group as part of this compound. So IR spectroscopy is used a whole bunch when you get into college. But as far as you guys need to know, it just causes vibration. Visible light is medium energy, so it excites valence electrons, so it causes that excited electron state from last unit. So it's used particularly to find the concentration of a molecule. It has to be colored. You guys have done this before. Like this is literally the spectroscopy with the little cuvettes. That's it. You use it to find concentration based off of how much light it absorbs. This also applies to low energy ultraviolet light, so UVA, low energy sections of UVA. High energy ultraviolet, which is UVB and parts of UVA, break molecules, so they straight up separate things. So you can identify elements or parts of a molecule that way by breaking them with ultraviolet light. It also is really nice because it sanitizes stuff, so it tends to destroy little germs sometimes if you dose it with high enough ultraviolet light. And then X-rays, same idea as ultraviolet. They break things, but they are even higher energy. So they remove core electrons. So they can affect even just elements. So not only do they break bonds, but they also start affecting core electrons. And that's that whole PES stuff from last unit. So the photon electron spectroscopy. So that whole like ionization of an element to figure out, you know, what its first, second ionization energies are. That's X-ray light. So that's kind of a breakdown for everything. So a few of these do tie into previous units. This goes back to concentrations with spectroscopy and those little cuvettes. These both tie into the last unit as far as identifying elements. But there's the whole general idea. I hope that's kind of just, we just want to introduce that to you. So I hope that kind of helps all this make sense. And that's it for me. I wasted enough of your time today. Have a good one and take care and have a lovely day.